The content we are learning today is the representation of functions. Firstly, let's review the learning content from the previous class. In the previous class, we learned about the three elements of a function: domain, correspondence, and value range. So, what are the representations of functions? How are the three elements of a function reflected in its representation? We will answer these questions in this class. Actually, we were introduced to three representations of functions in junior high school. Do you remember? That's right, it's the graphical method, tabulation also called tabulation, and analytic method. So in this lesson, we will first introduce these three representation methods through a few examples from the previous section of the textbook. First, take a look. The third question in the previous section is the air quality index change chart of Beijing on November 23, 2016. Since it is a graph, of course, the function should be represented using the graphical method. So what are the specific manifestations of the three elements of a function in this diagram? Let's look for it. First, let's take a look at this horizontal axis. The range of values for the horizontal axis is our domain t, which belongs to 0 to 24. So what is the range of values? How is the value range reflected? Observing the following graph, we cannot obtain the maximum and minimum values from it, and the specific values are not very accurate. The corresponding relationship is still not very clear, but we can know the trend of the dependent variable y with the independent variable x. This is the graphical method, and we provide a basic definition of the graphical method. The so-called graphical method is to use the value of the independent variable x as the horizontal axis and its corresponding function value as the vertical axis to depict each point in a plane Cartesian coordinate system. These points form the graph of the function. The method of using graphs to represent the functional relationship between two variables is called the graph method. The range of values for the independent variable x is the domain of the function. Next, let's take a look at the question from the previous section. 4. Table of angle coefficient changes for urban residents in a certain province of China. Since it is a table, of course, the method of describing the relationship between two variables using a list is called the tabulation. Let's take a look at what each row in this table represents. The first row is the year y, from 2006 to 2015. The angle coefficient in the second line is the value of the angle coefficient for the corresponding year. The value in the first line is our domain, represented by y. Y belongs to the period from 2006 to 2015. The second line should be the corresponding value range. So where is the corresponding relationship? The domain value range of the three elements of the function is reflected in the table, but the corresponding relationship is still unclear. We will provide a basic definition for the tabulation. The so-called tabulation method is to create a table with two rows and multiple columns. The first line is the value of the independent variable, and the second line is the corresponding function value. This method of using tables to represent the functional relationship between two variables is called the tabulation. The range of values for the independent variable x in the first line is also within the domain of the function. We have learned about the graphical method and the tabulation, but of course, the last remaining method is the function parsing method. Let's take a look at question 1 from the previous section. After accelerating to 350 km per hour, a certain Fuxing high-speed train maintained a constant speed for half an hour. The relationship between the distance traveled by the train and the running time t during this period can indicate y. This is a simple question of distance, and we can easily get such a relationship. Since it is a uniform motion, the distance is equal to the speed multiplied by time. Can this correspondence fully describe the functional relationship in the problem? It seems impossible. We cannot yet reflect this relationship in the corresponding relationship. That is to say, it cannot reflect the range of values for t. We need to add a domain after the corresponding relationship, which is the complete parsing method. That is to say, the analytic method contains two layers of meaning, the first layer being the correspondence relationship. The second layer is the domain definition. We will find that the parsing method is the only one among the three methods that can reflect the corresponding relationship. These three methods seem to have their own advantages and disadvantages, so what are their respective characteristics? We have gained a preliminary understanding of the three representations of functions through these three questions. Next, we will use three examples to further study these three representations. First, let's take a look at example 1. The unit price of a certain laptop is 5 yuans, and buying X laptops requires Y yuan, which is expressed in three ways. The function y is equal to fx, where x is 1, 2, 3, 4, and 5. Because its x only takes 5 values, we can calculate in our minds that buying 1 book costs 5 yuans, buying 2 books costs 10 yuans, buying 3 books costs 15 yuans, and so on. We can easily obtain this method for the list with domains of 1, 2, 3, 4, and 5. If I hadn't gone to sell 5 books, I bought 50 books. Can you make a list? What about buying 500 copies? 5,000 copies? So we need to use the tabulation to react first and use it to solve the problem. Its premise is that there should not be too much data. Next, let's take a look again. According to the definition of the list, the first row is the value of the independent variable, while the second row is the value of the corresponding dependent variable. What does each column represent? Actually, each column represents a point in the Cartesian coordinate system. So this is what we call the graphical method. By plotting these 5 points in a Cartesian coordinate system, we obtain its graph representation. The same domain is still defined as 1, 2, 3, 4, and 5. So let's observe this graph. Although it is as visual and intuitive as the tabulation, the horizontal and vertical coordinates of these points are not very precise. However, it also has its own advantages. It reflects the trend of the dependent variable y changing with the independent variable x. That is to say, in this question, the larger x, the larger y, which translates to the fact that the more books we buy and the more money we spend, it is certainly in line with our life experience. On the other hand, have you noticed that these 5 points are quite regular when observing this graph? It seems to be on a certain straight line. The process of listing just now shows that when we obtain the value of the first digit y in the second row of the table, we also need to use simple calculations. We abstract this process and obtain that y equals 5x. This x belongs to 1, 2, 3, 4, and 5. This is what we call the analytical method. This y is equal to 5x. Isn't it just a straight line? Returning to the last remaining issue of our graphical method earlier, those 5 points seem to be exactly on a certain straight line. Now I have answered this question through analytical methods, and it is indeed on this straight line. Then, 5 points on the straight line were localized. From this perspective, we will find that although they are called graphical method, tabulation, and parsing method, they all depict the same function from different levels and perspectives, and their essence is consistent. Of course, on the other hand, it also indicates that each method has its own characteristics. So, let's summarize the characteristics of each of the 3 representations of functions. Recalling example 1, let's identify the characteristics of 3 different representations. The first analytical method is of course very concise and abstract. Can I abstract all the functional relationships into such an analytical method? Actually, it's not. My corresponding law can only be abstracted when it changes regularly, so it must be regular. Of course, we cannot forget to define the domain, and putting the domain and its corresponding relationship together is the parsing method. What about the graphical method? The graphical method is intuitive, but not precise. The horizontal and vertical coordinates of each point may not be very precise, but they are generally available. It has its own characteristic, which is that it can reflect the changing trend of the dependent variable y with the independent variable x, which is its unique feature. So the tabulation is very intuitive. The values of the independent variables in the first row correspond to the function values in the second row, but it can only represent when the values of the independent variables are discrete, and the values cannot be too many. This is what we call the 3 representations. And no matter which one, we must not forget to add a domain. Next, let's take a look at example 2. Example 2, draw a graph of the function y equal to the absolute value of x. A classmate asked, it only has a corresponding relationship. Why is there no written domain? If not written, x is assumed to belong to R. Then observe that this is an absolute value function. How to handle the absolute value function? Then we need to go to the absolute value. According to the definition of absolute value, we know that when x is greater than 0, y should be equal to x. When x is less than 0, y is equal to negative x. Let's briefly express the paragraph we just discussed in terms of classification in this form. When y is equal to the curly braces negative x, x is less than 0, and x is greater than or equal to 0, this representation method is called the piecewise function representation method. So each segment of a piecewise function is a familiar function to us, and we can draw its graph based on the corresponding relationship of each segment. When it is less than 0, it is negative x, and when it is greater than 0, it is x. This is the method of numerical transformation. So let's take a closer look at what's going on with this piecewise function. From this question, it can be seen that the so-called piecewise function is actually a function whose domain is divided into several intervals, and in each interval, the function has different corresponding relationships. A piecewise function is one function, not several functions. Its domain should be the union of the domains of each segment function, which is a basic definition of a piecewise function. Let's go back to the question itself and draw a graph where y equals the absolute value of x. We can easily draw its graph by transforming it into a piecewise function. So, what information can we get from this graph? We need to leverage the unique advantages of the graph, which is that it displays the trend of the dependent variable y with respect to the independent variable x. It can be seen that when x is less than 0, the larger the independent variable x becomes, the smaller the dependent variable y. When x is greater than 0, as the independent variable x increases, the dependent variable y also increases. So, I want to ask this question: can you get these conclusions from the analytical formula alone without an graph? Of course not. If there is no analytical expression, do you know which function he is referring to just with this graph? I'm not sure either. So we can know that the analytic method is abstract yet precise. The graphical method is intuitive and vivid, and the two complement each other in order to better understand this function. This is the so-called combination of numbers and shapes. In other words, it is necessary to add analytical methods to the graphical representation of the three function representations, and use these two representations to represent the same function, in order to depict the function deeply and thoroughly, both intuitively and accurately. Let's further appreciate the idea of combining numbers and shapes through example 3. Example 3. The given function f(x) is equal to x plus 1. Gx is equal to the square of x plus 1. X belongs to R. Draw the graphs of these two functions in the same coordinate system. The second question is that any x belongs to R. Use mx to represent the larger of these two functions, and use graphical and analytical methods to represent this function. Firstly, let's take a look at the first question. To draw these two functions in the same coordinate system, which we are familiar with, this first question is relatively simple. Let's review the question and look at the second question. Using mx to represent the larger of these two functions, what does this size refer to? From the perspective of graph analysis, it should refer to the point with a larger vertical axis, right? We approach this question with these preliminary conclusions from the examination. Through the preliminary examination just now, we can obtain the graphs of fx and gx, where g and x are equal to x plus 1 squared, which is a parabola. Therefore, fx is a straight line. These are graphs of two functions that we are familiar with, which can be easily drawn. Next, we will stand on the steps of the first question and think about the question raised by the second question. We need to draw the larger of fx and gx, which means when translated into graph language, it refers to the one with a larger vertical axis, or the higher layer of the graph from top to bottom. Let's take a look at this picture, which means it's relatively high. It's probably this graph. This is the graph of mx, the larger of fx and gx, as mentioned in the second question of the question. Okay, let's observe that this graph seems to be composed of several segments. So the next question is how to write its analytical expression from its graph. We further observe this function, and in fact, the left side is still a part of the parabola. The middle is a part of a straight line, and the right is a part of a parabola. It has different corresponding relationships in each paragraph. This is the piecewise function we just talked about, which means that the analytical expression for this problem should be a piecewise function. The first segment is a parabola, the second segment is a straight line, and the last segment is a parabola. The key to listing the form of this piecewise function is to find these two intersection points. How to find the intersection point? That's right, to find the intersection point, we need to solve it by combining the squares of y equal to x plus 1 and y equal to x plus 1. To find these two intersection points, they are exactly -10 and 1. Can everyone write this piecewise function by finding the intersection point? When we look at the graph, when x is less than or equal to -1, it is the square of the parabola x plus 1. When x is between -1 and 0, it is the straight line y equal to x plus 1. When x is greater than 0, it is still the square of the parabola y equal to x plus 1. We merge these classification discussions into one functional relationship, which is the final piecewise function. Observe MX and pay attention to its format. It should be followed by a comma after the corresponding relationship in each paragraph. Write down the interval in this section, and the domain of the entire piecewise function should be the definite set of each domain, which means it should be all real numbers. So, our method of deriving the corresponding analytical expression from an graph is through the use of geometric auxiliary numbers. Next, let's summarize what we learned in this class. Firstly, of course, I learned 3 types of representation: analytical, tabulation, and graphical methods in terms of content. Their respective characteristics are that analytical methods are concise and abstract, but they cannot represent all functional relationships and must be regular. The biggest disadvantage is that they are not intuitive. The tabulation is quite intuitive, with the values of the independent variables in the first row and the corresponding function values in the second row. However, it can only represent when the independent variables are discrete and the data is relatively small. The graphical method is intuitive and can also represent the trend of the dependent variable changing with the independent variable. However, its biggest problem is its inaccuracy and incompleteness. The method of combining analytical and graphical methods to characterize the same function is the combination of numerical and geometric methods. The method of combining numbers and shapes is one of the most important thinking methods we learned in high school.